Hello guys, good morning. I hope you're all doing great. Today we're going to start this activity in which you're going to be watching a series of 4 or 5 videos, and after each video you're going to be answering some questions, okay? I'm going to try to be as brief as possible, but I need you to please make sure to take notes and pay a lot of attention to all the explanations that we're going to work, okay? So let's start by talking about polyhedrons. We already know what polyhedrons are. These are solid figures that are enclosed by polygons, right? Polygons. So when we talk about polygons, we talk about two-dimensional figures with only straight sides, okay? No curves, no circles, no semicircles. Now, when we talk about solids of revolution, these solids of revolution, let's remember, they are also solids, but they are not enclosed by polygons or by flat surfaces, okay? They are enclosed by curved surfaces. Why are they called solids of revolution? Because let's look at an example of them. Let's suppose we have a rectangle. This is a rectangle, and I'm going to take this point as my axis for my rectangle to start turning around, like in a circle shape, all the way over here. If I do this, the path of my rectangle is going to end up forming a perfect cylinder, okay? Let's suppose we do the same with the triangle. If I take a triangle and I start turning it around about this edge over here, it's going to end up forming a perfect cone, okay? Its path. So that's why it's called solids of revolution, because it's a solid and it's formed by the revolution or the turns of a two-dimensional figure, okay? Let's remember that all polyhedrons have um, specific parts that we've already talked about, but I'm going to go through them really quick, okay? Just as a way of reviewing this topic. So the first part that we have is this one, which is called the vertex, right? The vertex are all those corners in which three or more faces intersect. Now we have this one, which is the place where only two faces intersect, which is called the edge. And then we have the easiest one, which is this one. I'm going to do this one, which is the face. Okay, the faces. Those are the three important parts of the polyhedrons. And let's remember that there was this man a long time ago called Euler. He wrote the Euler's formula. He did it by finding a relationship between these three elements in all polyhedrons. He said that if we take the number of vertices in a polyhedron and I add the number of faces of the polyhedron and I subtract the number of edges in any polyhedron, I should always get the number 2. Okay? Let's go ahead and prove this. In this polyhedron, I don't know what kind of polyhedron is, but they are telling me that this is a polyhedron. I'm going to count the number of vertices. Here I have 1. Let me point this out for you. There you go. Here I have 1, 2, 3, 4, 5, 6, 7, and 8. So we have 8 vertices plus the number of faces, which they are 1, 2, 3, 4, 5, and 6 faces. So I've got 6 faces. Minus the number of edges, which I have 1, 2, 3, and 4 on top. 1, 2, 3, and 4 in the bottom, so I have 8. And the vertical ones 9, 10, 11, and 12. So I have a total of 12. This should be equal to 2. 8 plus 6 is 14. 14 minus 12 equals 2. And this is correct.